going to be looking at a scenario, a context that has to do with Fred and Andy's colt. A colt is a baby horse. So here's our story. On the same day, two friends each buy a colt. Now, both colts have a starting weight of 50 kilograms. After 1 month, they compare the weights. Fred says, my colt grew 10 kilograms. Andy says, my colt grew 20%. Now, another month goes by, they meet again and compare the weights. Fred says, mine grew another 10 kilograms. Andy says, mine grew another 20%. All right, so the first question says, what are the weights of the colts 2 months after they were bought? I'd like you to take a couple minutes here on your own and answer question number 1. And I'm just going to make a space here for Fred and over here for Andy's. Logan, would you share out what did you get for the 2 weights and how did you get them? Awesome, thank you. All right, so we have a slightly different process going on for Andy. So we're thinking about the difference between just adding 10 kilograms every month, which is what happened for Fred. So he ended up at 70. And what's interesting about Andy's is that after the first month, they actually both would be at the same weight of 60. Because to find 20% of a number, so 20% of any number, we're going to turn that 20% into a decimal, so we could turn it into 0.2 or 0.20. And then in math, of means to multiply. So we're going to multiply 0.2 times whatever the number is that we want to find 20% of. So what's super interesting is after this first month, like 20% of the starting weight of 50 is also 10 kilograms. So they both have 60, but then Andy's colt is now 60 kilograms. Then the second month goes by, we're going to take 20% of 60, and that ends up being 12, add that onto the 60, and we get this final weight after the 2 months of 72 kilograms. So Andy's is growing a little bit faster as we get to the end of that second month. Well, we're going to actually see what would happen, assuming this growth pattern continues for a period of 8 months, to see how the growths are happening between Fred and Andy. So we're going to continue to fill in the following table. If we look at what has been written so far, we can make sense of what's happening on Fred's side. Growing by 10 kilograms every month is simply adding 10 to the previous amount. So we already talked about that ending weight of 70 after the second month. And then when we take a look over here at Andy's side, so this is really similar to what we talked about just a few minutes ago, that we had the starting weight of 50. So we're taking 20% of the previous weight. We're adding that on to the previous weight, so that gave us 60. But now when we go into month 2, now the previous weight is 60, and then we're adding on 20% of 60, which gave us the total of 72. So I'd like you to go ahead and finish out this table. This is the part I thought your calculator would be helpful for. And I would love for you to show your work for each row of the table, similar to what has already been written. All right, so I'm going to go ahead and display my table up here. So you can kind of check in on your values and make sure that we were on the right track. Fred's side was definitely a lot easier and faster, just adding 10 each time. A little bit more work here on Andy's side. Also, I know that there may have been some decimals in some of these calculations, so I just did some rounding here, and you can do the same. So if you need some time to finish out filling the values in your table, you can do that now. But once your table is filled in, I'm going to have you go ahead and move on to part 3. So if you look over on the right-hand side of your paper, we have a graph, and you are going to graph two lines, one line to represent Fred, we're going to do that with a dotted line, and then the other line to represent Andy, we'll do that with a solid line. So you'll notice that we have months here listed on the bottom. For each value that we had in our table, the value that we calculated is going to be like the y value of the coordinate. So for example, like at 3 months, I would plot my point at 80 for Fred's line. At 3 months, though, I would plot the point at around about 86.4 for Andy's line. So the idea is for us to not only see the difference in the growth patterns here in the table, we can definitely see some differences in those numbers, but we're going to see how this shows up graphically. So finishing the table and then continuing, when you do have your graphs done for part 3, go ahead and also answer questions A and B, and then we'll stop there. We've got a little stop sign there. We'll come back together before we talk about the rest of the page. All right, so we just plotted the points there from our table, and so we see that not only did the numbers look pretty different in the table, especially they were more different the more time that went on, we're also seeing some differences here in the graph. So in part A, it says, what is the most striking difference between the two graphs? Just part A, Leah, would you share out what are some things you noticed here? Yeah, exactly. So it seems to be that there is not a lot of like vertical space between the points early on, but as we go later on, there's a lot of space if we think about measuring how far one point is away from the next. Christopher, what did you say for part A, a difference between the two graphs? Yeah, so we have talked a little bit about the difference between an exponential pattern graph and a linear graph. We did this back when we were looking at our scatter plots, and we had some real-world data that we had collected, and sometimes when it seems to kind of grow in sort of a bit of a curved shape, sort of like Andy's, this is a characteristic of exponential growth. When something is growing exponentially, if you've probably heard that term before, it means that it's getting really big, really fast. And so what's causing that curve is what Leah started with, is that those points are getting further and further apart. And if we actually look at what's happening here with the values in the table, it kind of makes sense why they're getting further and further apart. Because if you think about how much is actually being added from one month to the next, like first we only added 10 kilograms, then from the first month to the second we added 12 kilograms, then we're adding 14.4 kilograms, so the actual amount that is being added from month to month is getting bigger and bigger. When we look at month 8 compared to month 7, to get from 179 to 215, whoops, I just tried to subtract those, actually added them. We're adding 36 kilograms in 1 month. That's like a huge difference from what we were adding at the very start. So Andy's is a bit curved, and that is characteristic of an exponential pattern. The straight line that we have here on Fred, this is a characteristic of a basic linear pattern. So we've done a lot with linear functions throughout the year. This is where we talk about having a slope and a y-intercept. The slope is that constant rate of change. Just every month, add 10 kilograms. Another month goes by, add another 10 kilograms. There's no curve in there. It's perfectly straight because it's linear. All right, let's look at part B. It says, do you think either of these growth patterns is realistic for a longer period of time? Sean, would you share out what did you answer for part B? No, yeah, exactly. Eventually they're going to stop growing. So if they were to continue, we might have like 10,000 kilogram horses walking around, and that would be quite scary. So in the real world, growth of humans, growth of animals, there's going to be kind of a growth pattern, a growth chart that seems to grow for a while, and then when they reach a certain point, it's going to just kind of flatten out. So when they've reached adulthood, we don't expect the growth pattern to continue on forever and ever. All right, let's take a look here at this last piece. It says the growth of Andy's colt deserves a closer look. So we're going to take a closer look at the values here in our table for months 0 through 5 to help us write an equation that would tell us the weight of Andy's colt after any number of months, T number of months. So notice that if we were to, we're going to start by looking at what happens when we divide the weight this month. We're going to do the weight this month divided by the weight last month. And so we're going to look at that for each set of weights listed here in the table to try to figure out what is the relationship, what is the pattern from one weight to the next. We know that it's not a pattern involving addition because we're adding different values each time. So we're going to see what happens if we divide them. So let's just start here looking at month 0 to month 1. So we're going to do the weight this month. We're going to say at the end of month 1 divided by the weight last month. So we're going to start by doing 60 divided by 50. And notice how that is equal to 1.2. So one thing that we can say about that, let's add this into our table, that if we were to do 50 multiplied by 1.2, that would equal 60. And actually, I'd love for you to write that on the inside part. I want us to actually leave a little bit of space on the right-hand side of our table. So if we were to double check that here in the calculator, 50 times 1.2, sure enough, it's equal to 60. Okay, let's see what happens for the next set. So if we look at month 2 compared to month 1. So we're going to do the ending weight after the second month divided by the weight of the previous month. We're going to do 72 divided by 50. I'm sorry, 72 divided by 60. And look at this. Notice how that's also equal to 1.2. So that means that 60 times 1.2 is 72. I'll make another little arrow here. All right, let's check that for the next two values. So we're going to see what's happening from 72 as it's growing up to 86.4. So I'm going to do 86.4 divided by 72. And sure enough, it is equal to 1.2 again. So from 72 to 86.4, that is also 1.2. And the next two will also follow in the same pattern. If you'd like to check these on your calculator, you can. But it will continue to work all the way down that when you multiply the weight by 1.2, it's going to equal the next weight. All right, so we're going to see if we can use this to help us get an equation. So let's start with this first month that had an ending weight of 60. So the way we got to the 60 is we started with our starting weight of 50, and we multiplied by 1.2 one time. Let's look at 72. So I know it was doing 60 times 1.2, but to help us get to an equation, it's going to be helpful for us to think back to that starting weight of 50 and just think, okay, how many times have we multiplied by 1.2 to get up to 72? So we multiplied by 1.2 once to get up to 60, then we multiplied it by 1.2 again to get up to 72. Now if we look at the 86.4 and the starting weight of 50, we had to multiply by 1.2 3 times to get 86.4. To get the next weight after the fourth month, we multiply by 1.2 4 times. And to get our final weight, we multiply by 1.2 5 times. Space there. I'm wondering, would there have been a shorter way to write some of these out without having to have so many 1.2s listed. Jack, what else could we have done? Yeah, let's turn these into a form with an exponent. So I'm going to start at the bottom, just since that was the biggest, longest one. And I'm going to say, okay, that's really the same thing as 50 times 1.2 to the power of 5, because there's 5 of them listed out. Multiplying 1.2 by itself 5 times is going to be the same thing as raising it up to the 5th power. This is 50 times 1.2 to the 4th. 50 times 1.2 to the 3rd. This one is 50 times 1.2 squared, and technically this one here is 1.2 to the power of 1. 1.2 to the first power just means there's 1.2. Now, the interesting thing with the exponents here is notice how they're decreasing by 1 as we're going upwards in the table. If we were to do that one more time, our starting weight of 50 is actually the same thing as writing 50 times 1.2 to the power of 0. Anything to the power of 0 is equal to 1. This is an easy thing that you could always double check on your calculator. It doesn't matter what the base is that's holding up the 0. So that's kind of an interesting thing, that even that starting month follows the pattern, kind of the general format. All right, so we are going to turn this into an equation now, and I'm going to actually write this as a function. So I'm going to use a W to represent the weight of Andy's Colt. Now, to specify that I'm talking about Andy and not Fred, I'm going to use a little subscript of an A. And this weight is going to be dependent upon how many months the colt has been growing. So it's going to be a function of T, where T represents the time in months. It's kind of like function notation where we say f of x is equal to something. Here we just have w of t. Those letters remind us of the variables that they represent. And so for each one of these that we wrote out, we always started with that beginning weight of 50. And then we were multiplying the 50 by 1.2 a certain number of times. Notice that after month 5, it was raised to the 5th power. After month 4, it was raised to the 4th power, and so on. So the exponent is going to represent the time in months. And so I'm just going to use a little t there to represent the position of our exponent. Remember back from our statistics unit, the exponential function has x up in the position of the exponent. T is just another variable that we're using in place of x. Okay, now if we were to label some of the pieces here that we have in the different positions, I'd like you to first start by drawing an arrow underneath this W, and let's just define this to represent the weight after T number of months. Now, the significance of the 50 is that this is our starting weight. And we do have a special name for the number that it gets multiplied by every month. In this case, it was continually multiplying by 1.2. This is what we call the growth factor. That's what we multiplied by each time. And then T, in this case, the specific time period that it was representing was the number of months. So on this left-hand side here, Fred's colt, we saw in the graph that it was an example of linear growth. And specifically what was happening is we just added the same value every month. So I'd like for us to write that down here at the bottom. A characteristic of linear, add same value every time period, or every time x increases by 1. In our case, that was every month. Every month we just added 10. That was a constant rate of change because it was always 10 that it was changing by. And that's what made a nice straight line in our graph. Now, on Andy's side, let's go ahead and draw in a couple of these arrows. I know we talked about them on the other part, but let's go ahead and write in a few, like multiplying by 1.2, because technically that is what was happening to get from one number to the next. And so below this table on Andy's side, we're going to say this was an example of an exponential pattern. And what we were doing here is we multiplied by the same number every month. So we have kind of a big space here for our quick notes for today. So our goal here is going to be to summarize some of the important ideas. We're going to connect back to our learning target. So the first learning target we had today was to write an exponential equation to match a real-life situation. I'm going to write in here learning target number 1, exponential equations. Now, we saw an example of an exponential equation today that was modeling the growth of Andy's colt. What we are going to put in here is a more kind of general version of how this equation is formatted. So it's going to start with a beginning number. So I'm just going to put an A in that position. And then we use parentheses to show another number that's being multiplied by. So I'm going to call that number B. And then it's being raised up to the power of a variable. We used T in our problem to represent the number of months, but more generally it would just be like an X, where the X would go in the formula, would be up in the exponent. So notice how the X is not down on the ground, it's not being multiplied by B, it's B raised up to the power of X. That X is telling us how many times does that B get multiplied by itself, and then it's multiplying by A, which was the number in front. Now, to give a few general labels to these positions, we called that starting number before, we called it the starting weight for the context of Andy's colt. Generally, we refer to it as the initial value. So initial is another way to say that's the starting value, or that's the starting amount. And this is also when X is equal to 0. So for Andy's colt, it's when it had been 0 months, what was the starting weight? All right, and then the B. That is the number that the Y values multiply by every time X increases by 1. So for us, it was 1.2. We're continually multiplying by 1.2 every month. And the special name we have for that number in the equation is called the growth factor. All right, our second learning target is about the difference between linear and exponential. So we'll label it just like that, linear versus exponential. All right, so initially, to write out the differences between these two types of patterns, we're going to start off by saying every time X increases by 1, and I'm going to make a little dot, dot, dot. Whoops, where did we go? There we go. A little dot, dot, dot. for us to put in a few different possibilities for how that sentence could end. If the relationship is linear, the y values add the same number. If the pattern is exponential, the y values multiplied by the same number. So for the story with Fred and Andy's colt, when x was increasing by 1, that really was every 1 month that goes by. When the number of months adds 1, Fred was linear, adding 10 kilograms every month. Andy was exponential. We really multiply by 1.2 every month. And we saw in the story that 1.2 multiplication was really the same thing as growing by 20%. So we're going to talk a little bit about that connection in our last learning target. The other thing we saw, and I maybe just put a little sketch off to the side of each one, the difference in the graph is that the linear pattern is graphed as a straight line, whereas the exponential one is curved. So I just start by making a little x and y axis for each one. We'll be talking a bit more about graphing exponential functions on Thursday. But the basic idea is that they have a bit of a curve to them, and you need to understand that they're not perfectly straight. All right, our last learning target here for today was about understanding the relationship between growth factor and the percent increase. All right, so we're going to summarize this with the specific values that we had in today's story. So on this left-hand side, I'm going to start by rewriting the 1.2. That was used for Andy's colt, and we already saw that that number was called the growth factor. And then I'm going to have you leave a little bit of space over here on the right side. We saw that for Andy's colt, it was growing by 20%. So we're going to label this as the percent increase. Now, what we are attempting to look at here is what is the actual connection, what's happening in the numbers between the growth factor and the corresponding percent increase. Well, let's start with this direction, which is kind of how we did it in today's problem, is we started by, we knew that it was a 20% increase, and then we saw that that was really the same thing as multiplying every weight by 1.2. So what actually is happening, maybe we'll go this direction first. I'm changing my mind here. The idea is that we're going to have arrows going both ways. I changed my mind. Let's actually start with growth factor and talk about how we're getting it to the percent increase. So notice that from the growth factor, if we subtract 1, I'm going to write a minus 1. 1.2 minus 1 becomes 0.2. Well, 0.2 as a decimal, in order to turn that into a percent, we multiply by 100. If I were to write those steps off to the side here, let's see if we can have another way of showing this. The first thing we did is we subtracted 1. Okay, so we got 0.2. And then 0.2 times 100. Well, when you multiply by 100, it moves the decimal 2 spaces to the right, and that's how it turns it into a 20. So that's actually what's happening going that first direction. All right, let's try to do the other way now. So having the 20% increase, we want to turn it into a growth factor. Well, the first thing to get from 20 to turn it into 0.2 is we are going to divide by 100. So it's just the opposite of what we did going the other direction. 20 divided by 100 is 0.2. And then to turn it into 1.2, we have to add 1 onto it. Now, the other piece that I'd like for us to add in here is that the percent increase is what we use for a real-world story. So in the story of Andy's colt, it made a lot more sense to say that the colt was growing by 20% every month. We didn't say the colt was growing, had a growth factor, and multiplying by 1.2 every month. That would just be sort of like a weird way to say it. So in plain language, the percent increase is what we like to use. Over here, though, on this side, the actual growth factor of 1.2, this is what we used for the equation. So when we're writing out an equation and we want to actually show what the numbers are multiplying by every month, that's when we need the 1.2 in there. All right, so I will come back to this and leave that displayed here if you need another moment with that, but we're going to continue. We're going to take about 5 minutes to work through and try the check for understanding. So there are 3 parts, questions 1, 2, and 3. So let's go ahead and take some time to look at those and try to work through. So for question number 1, our starting value is always going to be that number out in front. The growth factor is the number that's holding up the exponent in our equation, so that's 1.13. And then in order to get the percent increase, this is where we're going to think about subtracting 1 and then multiply by 100. So it's kind of like turning 1.2 into an increase of 20%. This is an increase of 13%. Another way to think about this, if there's a 1 in front of the decimal point, is just to look at the part that's after the decimal and just turn that into a percent. So lots of different types of stories here, but one of them could have been a puppy that weighed 5 ounces, gained 13% every month. In number 2, if we divide the ending amount by the previous amount, we see that we have a growth factor of 5. We have a starting value of 3, so that's going to be the value here when x is equal to 0. So that will help us to get our equation. And then for part 3 here, exponential, if we have a percent increase every month. Linear is when our y values are just adding something every time x gets bigger by 1. Exponential is always if the y values are multiplying by something. Now notice how the y values are multiplying by a fraction, they're multiplying by 1/2. That's why they're getting smaller, but it's still a pattern of repeated multiple pieces.